Okay, good morning. My name is Espen Albrektsen. I'm head of system technology in Gassicure, which is a Draeger company. And today I will talk about agile embedded development under regulatory constraints. I will start out with a little bit of context. Who are we and what are we making? I will give you guys a quick introduction to IEC 61508, which is the functional safety standard. But from the viewpoint of a software developer. And then I will spend most of my time on how did we do this to be fast, developing this, and of course, safe. So, who are we? Gassicure, founded 2008 by Håkon Sagberg and Knut Sandven, spin-off of Sintef Technology, purchased by Draeger in 2015. So we are 11 to 14 people in Oslo and 14,000 in Draeger. So it's a slight difference there. We are using MEMS, so micro electromechanical systems, to make an optical sensor for hydrocarbons. That's our core technology. A normal sensor needs, up to 60 minutes from power up until it can start doing measurements. We can do so in 500 milliseconds. So this allows us, of course, to do nothing most of the time, which is a requirement for doing things on low power. Meaning we can do this on battery, meaning we can do this wireless, meaning we can do this and save complexity for our customers, right? They don't have to draw all these wires. And these are typically in explosive zones, so not drawing wires is a huge benefit. Also, the flexibility of where do you want to put your detector. Sorry. Is it topside or subsea? It's topside. So we're looking for gas that's not supposed to be there. And so we have released the GSO1, which is a SIL2 certified wireless methane and propane detector. We have also released the P6100, where we took the electrochemical sensors from Draeger and made those wireless. Those are already based on technology that is low power. And we are using industrial wireless standard, ISO 100 and wireless HART. And of course, we're currently working on the next thing that will be even better. That I can't say that much about, but we'll see something. Users are industrial locations needing safety. So our detector, I think the list price is around 8,000 euros. So this is not for your car or your cabin or your sailing boat. Quickly about the measurement principle, not because it's so relevant for the talk, but just because it's fun and it's a bit interesting. So the gold standard for detecting hydrocarbons is optical detection. So if you remember back to your physics classes, you remember about spectral lines and absorption. So this blue line here at the top is the spectral absorption lines for hydrocarbons. So you see that they all absorb lines around 3.3 micrometers. So basically, if you shine light and you analyze the frequencies in the light that you receive, if the 3.3 micrometers are missing, you can be fairly certain that there are hydrocarbons there. Because you do not want to sound the alarm because there's fog, right? There's a problem with light, right? It goes through everything. And you don't want to sound the alarm for the wrong thing. And the reason why the standard method of doing this needs a lot of time is that you have typically two light paths, one through a reference medium where you know there's no gas, and one through where you're trying to measure. And then you have all the problems with what if one drifts, or what if there are other differences between the two light paths than the gas you're looking for. For us, we use this MEMS that can dynamically switch the light path at 1 kilohertz, and we compare the area under the side bands to the central band, and so we have a natural zero adjustment. So from the outside, it looks like this, very, very industrial. Opening it up, it looks something like this. So we have a lamp.
How big is it?
It's about this size. Yeah. So we have a lamp here, shines out. So here is where there could come gas. This is in contact with what we're trying to measure. Light comes out, hits the mirror, goes all the way back. This is where we have our little MEMS chip that does. This is tried to illustrate here with the different colors. This toggles. So it's both actually a diffractometer, so it's both a frequency filter, but also it can decide itself which frequencies to filter. That's sort of the core concept of the detector. So just some background there. And I kind of think it's kind of cool physics, so I like to show it. So 61508, or IEC 61508, functional safety. Also, a lot of people who are in this realm call it just SIL. So we're talking about the safety intrinsic level. It's the industry standard for safety critical systems in the oil and gas industry, but there's also used a lot of other places. So the systems are classified then according to the safety intrinsic level, SIL. And the SIL level is really just a measure of the PFD, the probability of failure on demand. So SIL1, 0.01, SIL2, 0.00, etc. So it's just how safe do you need your system to be. So we operate in the SIL2 realm. So you getting to SIL3 and SIL4, you're starting to talk nuclear plants and things like, go really, really bad. So we are only SIL2, which is relevant for a lot of the things that we need to do and how much documentation do we need to do, what are we allowed to do, and there's lots of things around there. But the measurement is probability of failure on demand. And this is the probability that the system will fail when it is needed. Because the focus of 61508 is safety. And there's really only one illegal behavior for us, and that's to report no gas when there could be gas. So in functional safety, you talk about the safe state. So the safe state for us, it's perfectly okay to say, I don't know. I mean, our customers are not happy. But from a functional safety point of view, this is perfectly okay. So we must know that our measurement value is correct, or we say we don't know. And it's a process standard. So it's not so much about, so it's a process standard. It's put lots of requirements on how do we develop software. And in order to get a SIL certificate, which we have to have in order to sell our system, we have these assessors that come and approve our system. And they ask really, really tricky questions. Depends, it's a huge variation between the different assessors. Some are very focused on hardware, some are very on software, but they ask you very tricky questions. And in order to answer those, you have to have documentation. And we are software developers. We love documentation, right? I mean, that's our favorite thing. It's the bread and butter of what we do. It's documentation. Yay! But actually, most, if not all, of the requirements that the functional safety standard puts on us are really just software best practices. So for my team, it's really kind of that the best practices that I wish we all were doing are now compulsory and not optional. And if you do it right, it's not actually that hard. So in the SIL software process, there is this diagram. It's the V model. It exists in many different forms and fashions. Concepts are the same. So at the very top, you have your high-level software safety requirement. And then in the middle, you have your architecture and design. And somewhere at the bottom, you have your module. In this context, a module is a C file or a CPP file. And then you have tests verifying this. So taking back to the keynote today, right, the functional safety forces us to do this. Does not force us to treat these tests as equal citizens. So I took that away, and I think, it's a very good point, because maintaining this side of the picture is a nightmare. And it takes so much time. And it's very frustrating that you need to do some fix over here, which takes like 3 lines of code that you need to change. And then you spend a week figuring out why you broke all the other stuff. So it's a challenge. It's not that easy. The V model starts at the top. So you have the system requirement specification, which is verified by what we call system tests. And those are as close to the real system as possible. And the goal there is to verify the high-level behavior. So in functional safety, they also differentiate between verification and validation, but it's kind of the same thing. Then you have architecture and design, which is verified by your integration tests, where here the focus is to verify the interaction between subcomponents. Now, SIL is of course not a software standard, so this also talks about how does it work with your hardware, and it's just components here is a relatively general term. But we have hardware software integration tests where we also need to do fault insertion because we need to prove to the assessors that we go to panic or we crash, and we don't lie. We don't say 0 when we don't know. That's really the proof that we need to make. And also we have software integration tests. Again, focuses on behavior, but here it's also unexpected behavior. And at the very bottom, you have your unit tests. Wow, that's a lot of testing. And we need to do this before every release. I mean, that's a lot of work. Impossible to do this in a fast way, right? But wait, we all know about continuous integration. And the key to achieving an efficient development process is to automate the testing, right? Repeating all the tests, all the things that you proved yesterday worked, you don't want to repeat that test today. And so we created tests that automize the different levels in the V model. So we need several testing regimes. So we have the system test setup. Focus here is on the normal system behavior, limited ability to inject unexpected behavior, right? The farther up you go in your hierarchy, the harder it is to inject unexpected behavior. So then you have in the middle. We break our system in some way, depending on what the focus of the test is. We have simulator tests at the bottom, right? So these two run on actual hardware. The bottom one runs purely on simulator. And with a sufficient level of test automation, validation becomes trivial. Right? So this formal final step that you need to do before you release is just basically pull your logs from Jenkins and say, yes, tests are green. I can prove that this was executed. It's all done. You probably want to do some manual testing in addition, because there's a lot of things that it's just too time consuming or it's too complicated to automate, right? So for our case, climate chamber tests, so spinning the thing up and down in temperature, pressure, things like that, we don't automate. We know that our physical sensor is stable. We know it's been characterized. We know it. So in our build system, we're focusing on the continuously evolving part, which is the software, right? So before we make a new sensor, there's of course a lot of chamber testing, etc. But that's a different process, and it's a much slower process than the software development process. And also we only did very limited hardware fault insertion automation. We're considering doing it more on this project that we're working on right now, because here we have produced a needle jig, allowing us to make this easier. But for the GSO1, this was definitely a manual process where our electronics guy did, and he did short-circuited each capacitor and showed, yeah, we went to panic, and the assessors were happy, and then we only did that once because you don't change hardware that often, right? So the value of automizing it is smaller. And of course, you also need your long-running tests, right? I mean, we put our detectors out. They have a 2-year battery lifetime, a 10-year product lifetime. So obviously, we need it to be stable, right? And then one side can have 100 detectors, so it needs to be really stable. Because even a crash once a week scales very poorly if you have 100 detectors on a site. I've considered, making Jenkins do this for me. So every Friday, I take the last green build, push it out, and then every Friday collect the logs. But yeah, haven't gotten around to do that yet. So what does 61508 demand of us? Well, it's a short list. Yeah, well, it's not that short. So you have the columns here. It's the SIL1, SIL2, SIL3, SIL4. Required means recommended is you. Yeah, it would be nice of you if you do this. HR highly recommended is, yeah, you should do this. And NR not recommended, yeah, don't do this. Thing is, you're allowed to do it, but every time you break the recommendations for your level, you just need to have a good reason. So the more you break here, the more you need to argue in your meeting with your assessors. So it's perfectly okay. If you say, yeah, I know that you don't want me to use malloc, but I know that I'm doing it. Then if you're able to convince your assessors that you're doing it in a safe way, you can't get away with it. But it's just easier to follow the rules. And there are more of these. Yes. And there are more of these. And there are more of these. And this one is good. Test case execution from boundary value analysis. This is part of SIL2. So that's you have to look at your code and you have to say, okay, these are the boundary values of this function A, and you actually have to document that you tested all the boundary values. Yeah. Oh, froze. What happened? Oh, there we go. Yeah, and there are more of these. And there are more of these. But let's break it down. So 61508 requires us to review our design. Probably a good idea. We have to document that we reviewed it, which is boring, but still. Review our source code. Definitely a good idea. I mean, that's the most efficient way to find bugs, right? Have a colleague read your code. It's a really good idea. Unit test our code at 100% branch coverage. At this point, until this morning, I disagreed. I was going to say this is a really bad idea. After hearing this morning's talk, I'm not so sure anymore. But my reason for saying that this is a bad idea, that 100% line coverage is a code smell, is my position was that if you wrote 100% line coverage, you probably focused on writing the wrong tests. You focus on writing those tests that caught that last line of code when you probably should have focused on your boundary values. What are the things that can go wrong? What are the unexpected behaviors? Because it's typically quite easy to get the 100% line coverage. It's not that hard, especially since if you're using some instrumentation code there, you can just exclude this section because I know it's a panic, it's never going to happen, so I just exclude it. Yeah, then it gets really easy to get to 100% line coverage. But we have to. So it's not an option. But again, here, it's perfectly okay to break the rule. So we do not, of course, do unit tests for our hardware abstraction layer. Right? I mean, it's pointless, hard, and zero return on investment, right? And that's just, we argue that we don't do that because this is covered by our hardware-software integration tests. And then the assessors are happy. So it's perfectly okay as long as you have an argument and you play this with the assessors and they accept it, and then you can go on. So we have to execute software-software integration tests, execute hardware-software integration and system tests, and we have to document everything. Our favorite task. Is it still fun to have? Is it still possible to have fun while developing? Yes, at least with a good help from our butler. So, how to be agile and safe. So, we strive hard to keep as much documentation as absolutely possible inside our source files. Doxygen and conventions. We think that keeping the documentation as that close to the code significantly increases the likelihood of whoever changes something to actually keep the documentation correct. Still, you see that it spins off, but if you create a Word document, the only thing you know is that 5 hours from now, it's going to be wrong. Something is going to be wrong in that Word document, right? Slightly higher chance when you're changing the code that you also update your documentation. I mean, we're not that good at that even, but it's at least a little bit easier. And it's still the same tool, and you don't need to do the context switch. You can stay in your IDE, you can stay in your development environment and do both things at the same time. And then, because we have all these requirements on fault insertion and all these verification tasks, we, of course, we develop sensor simulators that can simulate it both expected and unexpected behavior of our sensor. And that's quite challenging. I mean, this is the pretty hard part of setting your system up. So this is an investment in your build system. of course, depending on the complexity of your system. We also add specific fault insertion code into the firmware in order to prove to our assessors that, yeah, this mechanism works. So one of many requirements that we have is we have to test the memory. So we have a memory checker, goes through every hour. We have to verify that all our RAM is still functional. So there's pattern, there's ways of doing that. You write ones and zeros, and you read them back, and you see that you got what you want. And so how do we prove to the assessors that this is actually working? And we did this with DMA. So we basically set up a DMA that just hammered this specific address. And then the test is that within 1 hour, our system should go to panic. It should detect that this part of RAM seems to be broken because I had a DMA continuously going on a timer. Same, we need to verify that the integrity of our binary is okay. So we need to verify the CRC of our flash. Same there. We inject code that intentionally tamper with the flash, and then the test is that within 1 hour we should go to panic because our flash is broken. All these hardware tests are slow. Yeah. You compile it, you need to push it to the target, you need to wait for some setup. Yeah, it's just slow, right? So unit tests, you want to be fast. So what we do, we use GCC and GCOV and the linker wrapping for unit and software integration tests. So for regulatory reasons, we need to use IAR for our embedded. So our target is compiled with IAR, but our unit tests are compiled in GCC. And then we use C# and several physical setups for the hardware-software integration tests. And then many of our formal validation tests are now trivial. You just inspect the Jenkins log and verify that the test executed and confirm that the behavior was expected. Why all the manual stuff? Well, because we can't really, if we say that a green build proves that everything is okay, then suddenly Jenkins is a formal tool and then Jenkins needs to be validated. So therefore we had this manual step that, yeah, we actually go into the test case and said, yes, I, Espen Albrektsen, promise here on the day of them, I read the log and it ran and the results were as expected. So it's just a way of getting around not having to certify your tools. Yeah. And so what I just said means that we're already on 2 different compilers. And that's really nice. One thing is that, well, 2 compilers find more errors and warnings than 1. It's surprising that the compiler that we need to use because it's sort of okay for SIL2 very often finds far less warnings than what GCC, which we're not allowed to do because that's not safe. It's open source, so it cannot be safe, right? It's a bit interesting, but yeah. So just having 2 compilers is a really huge benefit, and also it reduces our dependency on some specific software vendor, right? And we still have macros for doing cross-platform compilation, but at least now you need to make a conscious choice every time you have some IIR-specific pragma or whatever. At least you need to have a conscious choice, and it all ends up in the compiler abstraction layer.h, and there's one place where you say, okay, these are the things that I depend on, and these are the things that I need to care about. We're using the Catch2 unit test framework. So, I mean, Phil Nash is here somewhere. Yeah, I think that's a very, very nice framework. It has this nested section concept where you can have one test case take over where the other one left off. The assertion markers are great. I mean, as we saw today, we want a lot of information when a test fails, right? Because you want to be able to quickly go in. You don't want to have to spin up your debugger every time you figure out that the test fails. And it's also now very nicely integrated with CLion, so it's very easy to just run one specific test. So this nested section, for those of you who haven't seen it before, so you have a top, so it's classic buffer here that I can create. And then once the buffer is created, I can copy something into the buffer. And the whole point here is that there's no meaning in executing these subsections if the first one failed. Right? If I cannot create the buffer, obviously I cannot copy anything into it. And catch is very smart in that it'll always run this, and then it'll come here, and then it'll run this test section, and then go out. Then it'll run this and run that section, etc. So it just does the right thing. It does what you expect it to do. So it takes away a lot of the pain of writing setup functions and things like that, because you can just kind of write your thing down. Also lends itself very well to TDD, because I mean, this is, I start here. I mean, can I create my buffer? Yeah, I can create it, and then I create my H file and my class, and suddenly I can do it, and then I can see, okay, yeah, the initial conditions are there, and then I can just keep on going. So it also lends itself very well to that. I mean, there's lots of unit test frameworks are out there, but I chose this, and yeah, we're quite happy with it. It's a little bit hard sometimes to track where are you, which section, what are the precondition in this nested section down here. So that's a downside, I guess. It's also very easy to write your, well, it's possible to write your custom matcher. So for us, the process value is a very prominent member in what we do. And so it's nice to be able to assert on the process value in a domain-specific language, if you will. And Catch supports this. You write this PV matcher, inherit this from some Catch matcher base, and you can do your own thing here. You can write your own describe, so you can output as much text as you want to make your test failure be meaningful. You can also have shortcuts for, yeah, if this happens, I want my process value to be bad, right? And then you can shortcut this, and then in your test, you just check that result.pv is bad. Very readable. And this has a very big benefit, because it means that you don't need to be a software developer to review this test case. So I often have my physics, my sensor team, review at least parts of our unit test, because this is where we do a lot of the decisions, right? This is our basically, some level, our unit tests are a design specification, right? So I find it's really worth it to take some time and really evolve into a domain-specific language. We should do it more, but we do it a little bit at least. But then we need to also have software integration tests. And yeah, are you mocking me? So we need a way to execute our production code in different ways, right? So obviously the module under test should not be modified. And for a unit test, you want to isolate dependencies. So yeah, there's all kinds of meanings on what a unit test is and isn't. I think it is what you want it to be. So it should be as unity as you need it to be. So you want to isolate the relevant dependencies for your unit test. But for software integration tests, you want to verify that your interactions are correct. And also there, test doubles come into place somewhere, right? Because we are depending on hardware. So we want to, somewhere in our system there are test doubles. So for example, for our sensor, we inject fake data from a real sensor, very low in our software architecture, and then propagates all the way up, and then we assert that the output is as expected. Because the problem with test doubles, right, it makes assumptions about other system components and allows us to test one unit in isolation, which is great because it's fast, well, easy, at least hopefully easy to understand why a test fails, because it's very isolated. And it is easy to inject error conditions. And we don't need real hardware. We don't need for this compile, flash, wait for boot cycle. But test doubles can get very complicated. And they can get hard to maintain because they very easily tend to be very tightly coupled to the implementation that they are faking. And they need to make assumptions, right? So if those assumptions are wrong, your tests become pointless. It gives you false pretense that everything is okay. And they don't run on actual hardware. It's both a pro and a con, right? Because it means can have different endianness. It certainly can have different integer size, right? So also things, optimizations can be different. For us, optimizations definitely is relevant because we're even using different compilers. We're using GCC on one side and IR on different on the target, which is potentially dramatically different, right? And there again, our get free out of jail card is the but this is proven by the integration test, the system, the hardware test that we run. Those are the ones that prove this. But yeah, I wouldn't be that shocked if there were assessors that would go, yeah, I don't like your solution that much. But ours so far have accepted this. And for sure, timing, right? It's obviously wrong on your unit test and your software integration test. For good and bad, right? So we need to evaluate how much battery do we have left, right? And this needs to run every 5 minutes. That's the way it goes. And that's a really long test, right? Oh, yeah, I'm going to run my unit test now. It's 5 minutes. Yeah, let's grab coffee. And oh, yeah, it needs to have 10 measurements because we need to suppress some noise. Yeah, well, in your unit test, you can speed this up, right? You can fake time. You can make time go fast. Very nice. So how do we do this with dependencies? How do we deal with dependencies? Because that's the difference. In my head, at least, the difference between unit test and integration test is how much of the dependencies do you muck away, right? And so what we chose is, of course, a number of mechanisms. So number one is just linker substitution. So that means that when we compile for unit test, we link in some code. If you compile for target, we link in some other code. So the obvious test double is that for unit test, we link in a fake hardware abstraction layer. So obviously our code depends on hardware, but for our unit test and software integration test, we just import a fake hardware. So it implements enough that the linker is happy, but typically those are just empty functions that do nothing. But they don't need to be. Right? So for example, we have a very complete UART mock that fakes UART, where I can inject bytes and I can verify that everything else is communicating correctly, for example. So it's up to you. It depends on your setup, what you need to do there. For C-based projects, we use a linker trick from GCC. I'll show that on the next slide. And there our test doubles are either fakes or stubs. So yeah, fake pretends to be something and a stub just does nothing. That's kind of the... And then for our C++ based project, so basically we switched all our embedded development over to C++. So there we do use the combination of service locator for things that are global, like your config, your BSP, things like that, and constructor injection. And then since we're using Catch2, I asked a little bit around what works well with Catch2, and some people said that this Trompe framework is great, and so we started using that, yeah, quite happy with that. I'll get back to the details on the next couple of slides. So linker wrapping, mocking in C. Mocking C in C, it's hard to mock, right? Because most mocking frameworks rely on virtual functions, right? So you inject a virtual override that does something else than the original. That's the typical mocking framework in C++. Well, virtual functions don't exist in C. And our code base was 100% C up until a couple of years ago. But the GNU linker has this -- wrap option, which is awesome if you haven't seen it before. So it's very easy. You say to the linker, so you compile your C files like normal. So there's zero touching of the C files. But then to the linker, you say, hey, linker, so the -WL is, this is an argument to my linker. And then the -- wrap is which argument to the linker is it. And then comes the payload. So, hey, Mr. Linker, if anyone wants to call sensor get output, please inject some code for me there. And then what happens is that the linker will replace the call to sensor get output with a call to --wrap underscore sensor get output. And you actually, with this linker argument, you get a linker error if you didn't implement this wrap sensor get output. And this, of course, lives only in your unit test. This is not in your production code. This is live in a separate folder, and it's there. And it also renames the original sensor get output. So what happens is that the linker renames the original sensor get output with this --real sensor get output. And this allows me to have a state variable in my test framework where I can say that the sensor mocks are enabled, then mock it. If they're not enabled, call the actual function. So this allows me to, on a test-by-test basis, decide if I want to just get the mocked data or call the data. So it means that I can compile all my unit tests into one single binary. I can run all the unit tests once, and it just runs. Yeah, and then of course you need a setter to set the fake value somewhere. This could also be a global. We have all kinds of patterns for this. Yeah, so it's a pretty neat trick. So if you're on GCC, you can use it directly. If you're not on GCC, well, having cross-compiler support is a really good idea. C++, much more to choose from, right? There's like tons of different frameworks. I'll just quickly show what we use. We use the Trompe. So yeah, the downside is that all the classes that you want to mock, they need to have virtual functions. And of course, we don't like virtual because it is overhead. And also from a functional safety perspective, yeah, well, the vtable is a pretty long-living variable. There's function pointers. There's all kinds of things that our SIL accessors don't really like. So I just came up with a very simple, dirty hack. I'm sure there's a prettier way to do this, but I basically made this testable macro, which means virtual if it's a unit test build, and then if it's not a unit test build, it's nothing. It's like it's not there. Yeah. And then that means that in my production code, I have to prefix it with something. I could have made it very small and disappear, but I figured it was okay that it's there. And then it becomes virtual, means that I can use Trompe to make a mock. And so here we have a mock of the optical system, which has this run measurement. And what's really nice with mocking, if you haven't used mocking frameworks, is that you can not only fake the return values, but you can also assert on the input parameters, and you can also assert on the sequence, etc. So it's really a powerful tool. But again, it is some maintenance, and it is very easy to end up too tightly coupling things. But for example, in an embedded system, it is really important to validate not only that things were called, but that they were called in the right order, right? You need to power on the ADC before you can read data from it, that kind of thing. And that's very easy to do. And once you get your head around the syntax, you can write some really good tests there. And again, we do not depend on real hardware. So these are fast, right? You can run this test iteratively. And then integration tests. Well, why do we need them? We already have 100% line coverage. Surely we don't need that as well. We even have boundary value analysis and test execution based on equivalence classes. Yeah. Well, unit test mock dependencies, right? What if the mock is wrong? Timing, definitely relevant here, right? And the focus is different. Right? The integration tests verify the interaction between the components. So we have two types. We have the software integration tests still running on emulator. Here, it's very useful for the C-based that we have this mocking where we can turn the mocks on and off. Turn the mocks off, it's a software integration tests. Turn the mocks on, it's a unit test. Very flexible. And then we have the hardware-software tests that are running on real hardware. Yeah. So for example, a communication stack, right? So we can mock the serial port hardware. we can inject a buffer with some bytes, and then it can go all the way through the system, all the way up to the application, maybe come back, and we can verify that the payload and the response is correct or whatever. And it's really good if your goal is to get line coverage. It's very high payoff here on number of lines covered by a software integration test, right? Because you exercise so much of your code, right? All your happy flow. And it's really nice, right? You validate a lot of your happy flow with one integration test. And it's pretty important that our happy flow works, right? So it's really valuable, and it's fast. You get instant feedback without having to push to Jenkins and wait for your nightly build to execute whatever thing, right? So it's valuable, but tend to be brittle, right? So one change somewhere, and then the CRC changes. So the version number changes, and suddenly the CRC changes, and your test had the CRC and its validation and everything. Yeah. So it's harder to maintain, and it's certainly sometimes very hard to understand why something fails. But if you run your tests all the time, then you haven't changed that much. So it must be one of the things you changed, right? Hardware-software integration test here, the focus is on the complete system. Yeah, and here we include timing, right? Interrupts, DMA, real-world sensors, maybe emulated sensors. And here, of course, it's important that this is the binary that we will ship. Maybe it's instrumented with some extra fault insertion things, but it needs to be the real binary. Otherwise, the potential differences between your GCC binary and your IAR binary, with and without optimization, different, blah, blah, too much, right? Well, I would accept the feedback from my assessor saying that, no, you can't do that, right? This is fair. So now we're getting very close to user acceptance tests, depending on how our test setup is, right? But much lower. Flash, boot, enter some stable condition, and dependencies on so many things. You have USB controllers, you have serial ports, you have wireless gateways. Our wireless gateways are, so the industrial wireless standards are probably good, but they're slow. I mean, they're meant for very static systems, right? So it can easily take 15 minutes from power up until we even join the network and start talking to the gateway. So it's nightmare. And Bluetooth and SD-Link, and so many of these tools that our continuous integration system rely on are not built for that purpose. I mean, how often do you need to take your USB line in and out of your SD-Link to get contact, right? Well, when this happens on Jenkins, well, someone needs to go into the build room and fix it. So it's complicated. This is hard, and I find that I've spent too much time on managing this side of our build system than I would like to. So here I really wish that we had a better process. And of course, you've lifted yourself up the V model, so now a failing test here is even harder to understand why it fails at this point. Yeah. So when we had one product, our test bench looked something like this. Now we have slightly more, and we need to, our guy who keeps things cleaned, he had got a baby, so he's been on paternity leave, and you can see what happens when you let software developers do this kind of thing. And we're a wireless company. What's up with all these wires? But yeah, so we have developed two concepts. We have the system test setup where we keep the hardware as close to production as possible. We don't want to muck around with it at all. We want to be very close to the real hardware that we actually are going to ship. And this is very efficient for the happy flow. And then we have the integration test setup where we build these sensor emulators that allow us to inject unexpected behavior. For GSO1, we could do it very controlled. We had a digital interface that we could hijack. We could emulate the digital lines. So there we could do very good injections. For our new system, it's because the design, the hardware design is different, so it's a bit harder to simulate, but still we can do so. And this allows us to inject the unexpected behavior, which is of course important. So we have currently 3 different wireless solutions. The ISO 100, we have 2 hardware platforms. The Murata thing went obsolete 2 weeks after product launch. Yay. So we have the Sentero. And we have 2 different sensor technologies. But we also have a very modular design. So there's a lot of reuse between products. And this communication module is, of course, central in all of these systems. So we needed a mechanism to reuse test cases and test hardware. So for this, for historical reasons and also because I like C#, we chose C#. And then we are using the NUnit framework. You could do exactly the same thing in PyTest. All the same concepts are there, but we chose C#. One of the benefits is that means that our integration tests share the code base with the UI tools that we use, because talking to our thing requires tools. You need to do things. And then we have a very solid, well-tested low layer that's shared between our development tools, some of our production tools, and our integration tests. So the base layer is very solid. So that's one benefit of this. But for C#, it's much harder to get people. So, but how do we do this code sharing of tests between test runs? So the NUnit test category is a mechanism to do this. So, and then on Jenkins you have nodes, and nodes can have labels. So in the test case, you decorate. So this was in Python would be an attribute, I guess. So you decorate your test case with requires GSTox and gateway of the Yokogawa type. And then in your Jenkins, you configure a node, and this has a GSTox hardware, and it has a Yokogawa gateway. And then in your Jenkins file, you combine test case filtering with node selection. So for those of you who don't know Jenkins, node means please Jenkins, give me a node that I can run my test on. And this node needs to satisfy some filter that I need to get my node. Then I have compiled my binaries somewhere else, so I need to get those onto the hard drive. And then I filter the tests that are relevant for this node. And then we create a number of test setups. Oh, this was too small. Oh well. So test category is requires suite Sentero ISA. Needs to run on a node that has suite and sensor emulator and Sentero and ISA 100. So this is where we map. And then we have one binary with all the test cases. We push to Jenkins, and then this spreads out onto many different devices, and we start to run our tests. I have until 12:40, right? Yeah. So we have 3 build types. We have merge tests. So every time it pushes to a feature branch, we do something. We don't run the complete test suite every time we push to a feature branch. So in my opinion, a feature branch should build in 15 minutes. Because you need the feedback to know, am I good? Unfortunately for us, that's not feasible. So I think our feature branch is now on 30 minutes. But still, relatively fast feedback. This is a balance, right? Because the shorter the fewer tests you run on your feature branches, the higher the likelihood it is that you break develop when you merge it into develop. So it's a trade-off, right? It also depends how bad is it that you break develop. So I have a relatively small team, so breaking develop is not good, but it's also not that terrible. I think it's how much do you want and how many levels do you want to do before you merge is a function of the size of the team and the complexity of the product that you're building. But we also have the concept of the full build, which runs every time we merge to master or to develop. And here we do everything except long-running tests. And then we have the nightly build, which runs all the tests. So we have this guest test selector for build type that basically returns this test category filter thingy. So if it's a nightly build, well, there's no filter, run everything. If it is a full build, so master or develop, we do everything except, so this not tilde thing is yeah, .NET test thingy. So everything except test duration long. If it's a feature branch, I want to run all the tests that have been intentionally marked as this test is so important that I don't want to merge to master to develop unless this test passes. And this was the case until, well, actually just a couple of weeks ago. And then, because the thing is that very often, yeah, you don't want to break any of the merge tests, but also I'm working on this new feature. Right? I'm working on this specific feature. And of course, I would like to have the test for this feature to also run before I merge it. And what ended up was people were then decorating their test with merge test. And then, of course, forgot to remove the merge test before merging to develop. And then the list of merge tests grew and build times go up, or feature build times goes up. Doesn't affect the develop build, but it does affect the So then we came up with a very simple scheme where we say, okay, so if you name your branch in Git to start with the issue number that you're working on, and then you mark your test case with a Jira issue, then it'll do all the merge tests and the tests that are marked with this issue that you're working on. It's quite easy pattern, really. And it also has another benefit. It means that in the test case, it's documented, why did I write this test case? So you link your test cases to Jira. So it can also be easier to figure out why did we do this. So it's that too. It improves your documentation and it yeah. Doxygen. Well, hopefully you all know that. Handled by most IDEs, and just having Doxygen and using it is really valuable, because with the modern IDEs you get so much extra information just by your hovering your mouse over your code, right? But it can also be extended through this alias function, and this is what we do. So for example, a link to a requirement, so TSR link, and then I red lighted this one, so you can reuse this. So this is a link to doors where we have our requirements, and you can also then easily in your Doxygen, you can just do TSR link, and then you write the ID of whatever requirement that you're implementing, and then the Doxygen will automatically generate a link that you can click and you can go to the requirement. We can also link to the design. So SRS implements. And why did we write this function? So yeah, so the update LED, well, it was implemented because it implements the LED fault 001 requirement. And we can document that we unit tested this. SRS verifies LED fault 001. So this unit test verifies that we proved that it worked. And we integration tested it. Same SRS verifies, just a comment in the C# file or your Python file, doesn't matter. And the alias behind this /SRS verifies is an xref, which is a Doxygen feature that automatically generates these tables. So all this whole table, this clickable table, is miraculously just generated by Doxygen because it's an xref. And I said that we love documentation, right? When it's auto-generated, right? That's really nice. We didn't need to do anything. Jenkins does this every time. And the unit test, same thing. Test case, status LED. It's implemented in status LED test CPP. So when your assessors come and ask, did you unit test this function? Well, let me check. This is my Doxygen. Click, 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 click. And yeah, it's on line 12 of status LED CPP. So, remember SIL2 and all those requirements? Well, we now have the requirements in some kind of traceable format. That's outside of what we do here. That's doors, or actually for GSL1, we wrote our own database in Django. We have the unit tests. We have a test report on Jenkins proving that the unit tests were executed. We have the integration test and the test report on Jenkins. We have the system tests. We have a generated Doxygen. And we can now focus on developing code and tests and not on maintaining documents and manual test reports. So that's how we do it. Questions? Yes?
What would you do if you would get more products? Like how would you scale this if it was
Yeah, it's a very good question. I mean, so it depends on how much you share, right, between the products. So it was a very hard discussion internally to go for one repo or many repos. We went for one, which explodes the integration test efforts and the number of times that my build fails because I push something on one product and then for some other reason it fails on the product that I know I didn't touch. So this is a challenge. But yeah, so it's a balance on how do you separate your project, I think. But the anything that you have that you can reuse, you have this pattern, right? The test selector and the node selector. So here you can do a very high level of sharing. If your communication platform stays the same, maybe you can just reuse all your integration tests for communication. Is that an answer to your question? Other questions? Yep. Up.
Did you create the software in increments, feature by feature?
Yeah, well, there's two sides to that story, to that answer, I guess. For GSL1, there was actually a working product that we had to throw away and then do again for SIL2 because it was impossible to get it approved because of the process standard requirements. So GSL1 was, but a lot of the tests were added after the fact. For what we're working on now, it's kind of a feature by feature. Yeah. But a lot of the concepts in our integration test concept is evolved over several years.
What about the hardware? Is the hardware finished before or?
No. So if you notice here on the test setup here, it says where is it? It's on GSTalks revision 8. So so we've had. There's also a nice thing with the filters. If you need to run your tests on several hardware platforms, it would simply, so let's say everything seen from the outside, revision 8 and 9 were identical, right? Which is the case for us because we have this Sentero hardware and the Murata hardware that are from the outside 100% identical, and then we can just run the exact same tests on both targets. So there's somewhere here there's requires Sentero and somewhere that requires Murata. And it's the exact same test cases are executed on both platforms. And if it fails on one, not the other, it's a big surprise and shouldn't happen. But at least we will know it. Yeah. Question? Yeah.
Yeah, two questions. I asked for the physical size, but can you also say something about the size or complexity of the code base?
Oh, I should be able to answer that question. I don't know. No, sorry, I don't have that off the top of my head.
Next question is, what about the cycle time from you decide to do a change? How long does it take until you feel comfortable that you have it broken?
Yeah, well, I mean, yeah, of course it depends on the change, right? But we have made some trivial changes. So I think our record from change request to release software is 2 days. But it was, to be fair, it was a very trivial change. But we did get everything executed and all the so we're still, there's a very formal process for change management. You have to do impact analysis, blah blah blah, lots of things you need to do. But since this was a very small change, we were able to do it very quickly.
Yeah, so that was end-to-end. But as a developer, when you do a small fix while developing things, you get this warm fuzzy feeling that yes, I'm ready to do another change.
Yeah. Yeah. Ties back to this problem with the number of dependencies that our build system has, right? So getting a green build is unfortunately currently way too hard. It's so many dependencies. We're unable to establish the wireless connection. Should the test then be green? Should it be yellow? Should it, yeah, how do we deal with that? So I currently feel like it takes too long. I feel that too often I implement the fix in an hour or two, and then I have to wait 2 or 3 days until I get everything in. Yeah, but yeah. Other questions? Yeah.
Just one. What's kind of like the next step for you? Is this like the perfect setup for meeting the 508, or is it? Do you have something in the pipeline for new technology?
Well, I mean, I think in terms of process and to address the time pressure, I at least would like to be more intelligent in selecting which test to execute. So if this part of the code was not touched, let's not run those tests. That could save time, but also it means that if you have an unstable test in this side and I'm working here, then I can still work here and I can still merge my stuff. Because in practice, that's what we do, right? We keep on ignoring tests because we say, yeah, it's not my fault. And from experience, yes, sometimes that is the right thing to do. But from experience, we have had several times where we ignored this issue because it wasn't my fault. And it wasn't this change to documentation.h, right, that broke this feature over here. But the fact that that feature broke was actually a real bug. So it's complicated, I think.
For like the setup now, if the assessors are like accepting kind of your output now,
yeah,
and then you would add some more technology, and they're like, we don't like this. So kind of, is this the sweet spot that you want to be in for many years, or is it always evolving to something new and better?
I feel that the concepts that we have had have been pretty stable over quite a few years now. So I think it's a good balance. We have the unit test where we try to focus most of our time, and then we have these two concepts of hardware testing that in total, yeah, feel like the right level of testing. Yeah.
When you're running software hardware tests, are you testing the hardware under different temperature? Because timing might differ, but
yes.
If it is cold versus hot.
It's a good question. No, the short answer is no. Of course you could, but then test times would really explode. But for sure, doing the nightly build in a climate cabinet would be relevant. But of course, then it gets even harder to understand why the test fails, and how do you, yeah. So tests. You have a test sequence, and something decides the order of testing, and tests Z down here. It always runs at 85 degrees, and yeah. So how do you? It gets complicated. So what we do? We do more manual characterization of temperature dependencies. But for sure, this is a very relevant question because, for example, we forgot to calibrate our bootloader clock, and then suddenly, for some reason, our physics guy wanted to flash a new release that I made at minus 40 degrees, and it didn't work because the synchronization of the clocks was wrong. So yeah, it's definitely a real issue. Okay, thank you for your time. Ja, det er jeg. Ja.